The process of hair turning white or gray over time has a name: achromotrichia. The word achromotrichia is a compound term derived from ancient Greek roots. A prefix meaning not, without, or lack of, which denotes the absence of color. Chroma, meaning color or pigment, which refers to the color melanin in the hair. Thrix, genitive trichos, meaning hair, which refers to the hair itself. And ia, a Latin suffix borrowed from Greek, used to form nouns denoting a condition or state, which denotes the condition or state of having unpigmented hair. So the term achromotrichia translates to the condition of hair without color. Achromotrichia is a natural consequence of aging. What does it mean to be a natural consequence of aging? Of course, it means it is an expected, non-pathological, and nearly universal biological change that occurs simply because an organism has lived a long time. How do cells know that the body has aged? The organism has aged. There are two primary non-negotiable molecular mechanisms. The first mechanism is telomere shortening. Telomere shortening is the most direct and precise cellular clock. Before getting into that, telomere comes directly from ancient Greek, perfectly describing its function and location. Telo is from ancient Greek telos, meaning end, limit, or completion. Think of words like television or telephone, referring to distance or ends, and mere is from ancient Greek meros, meaning part, section, or unit. Think of words like polymer or monomer. Telomere literally means end part or end section. Telomeres are specialized structures found at the ends of your chromosomes. They cap the end of every one of the 46 chromosomes in a human cell's nucleus. They are made of repeating sequences of non-coding DNA, specifically the 6-nucleotide sequence TTAGGG, repeated thousands of times. The DNA sequence is associated with specialized proteins that bind to it, forming a protective complex called shelterin. You can think of telomeres like the plastic tips on the ends of shoelaces, aglets. They serve two essential protective functions. Telomeres protect the actual genetic information, the genes, contained within the chromosome from getting damaged or lost during the cell division process. Without telomeres, the ends of chromosomes would be quote-unquote frayed and degraded. They prevent the ends of different chromosomes from mistakenly sticking together or fusing. The cell recognizes an uncapped chromosome end as a broken strand of DNA that needs repair. Telomeres signal to the cell's repair machinery that this is a natural end, not a dangerous break. The main reason telomeres are central to the discussion of aging is due to a phenomenon called end replication problem, which dictates how cells count the passage of time. When a cell divides, its DNA must be perfectly copied. The enzyme responsible for this, DNA polymerase, can only synthesize a new strand in one direction. Because of this directional limitation, DNA polymerase cannot completely replicate the very end of the linear chromosome. A small segment at the end is left uncopied. Therefore, with every cell division, the telomere gets slightly shorter. This is a built-in, non-negotiable consequence of how DNA is copied. Normal human cells can only divide a finite number of times, typically around 40 to 60. This limit is known as the Hayflick limit. Once the telomeres reach a critically short length, the cell interprets the exposed, unprotected chromosome ends as DNA damage. This signal triggers the cell to enter cellular senescence, which is irreversible growth arrest, or undergo apoptosis, programmed cell death. This is a vital mechanism to prevent damaged cells from dividing uncontrollably, which is a hallmark of cancer. In summary, telomeres are molecular countdown timers that force a cell to retire after a specific number of divisions. Their shortening is a direct, intrinsic mechanism by which the body, quote-unquote, knows and initiates the consequences of aging, such as the exhaustion of stem cells that lead to achromotrichia. The term telomeres was coined in 1939. 1939 was the year in which, on September 1, Germany invaded Poland. This act is universally recognized as the beginning of World War II. This invasion was executed using the tactic of blitzkrieg, lightning war, which involved rapid, coordinated attacks by tanks, motorized infantry, and air power. This was the culmination of Adolf Hitler's expansionist goals. The immediate pretext was a staged attack on a German radio station, but the real goal was Lebensraum, living space, in the East. The swiftness and brutality of the campaign immediately demonstrated that this war would be different from World War I. And on September 3, 1939, following the invasion of Poland, the United Kingdom and France declare war on Germany, officially commencing the global conflict. This declaration ended the policy of appeasement, which British Prime Minister Neville Chamberlain had pursued with Hitler in the preceding years, most notably at the Munich Conference in 1938. Britain and France had a defense treaty with Poland. While they declared war immediately, they did not launch a major ground offensive against Germany in the West. This initial phase of inactivity was dubbed the Phony War, a period of waiting until the fighting escalated in the spring of 1940. August 23, 1939. The Molotov-Ribbentrop Pact, German-Soviet Non-Aggression Pact, is signed in Moscow, shocking the world and secretly dividing Eastern Europe into German and Soviet spheres of influence. This pact was a non-aggression treaty between two bitter ideological enemies, Nazi Germany and the Communist Soviet Union. It stunned the world because Hitler and Stalin were expected to fight each other. The pact contained a secret protocol that divided Poland, Finland, the Baltic states, Latvia, Lithuania, Estonia, and Romania into German and Soviet spheres of influence. This guaranteed that the Soviet Union would not interfere when Germany invaded Poland, giving Hitler a critical green light. March 15, 1939. Germany annexes the rest of Czechoslovakia, dissolving the nation. This was a direct, violent violation of the Munich Agreement signed just 6 months earlier, which Hitler had famously promised would be his, quote, last territorial demand in Europe. The annexation completed the German takeover of Czechoslovakia. The first step was seizing the Sudetenland, a border region with a German majority, in October 1938, which the Allied powers, Britain and France, allowed under the policy of appeasement to avoid war. When Hitler marched into the remainder of Czech lands, Bohemia and Moravia, he demonstrated that his goals were not limited to uniting German-speaking people, but were purely based on imperialist conquest. This event proved to Britain and France that appeasement had failed, hardening their resolve to stand up to Hitler when he invaded Poland later that year. April 1, 1939. The Spanish Civil War ends, with Francisco Franco declaring victory, initiating a long period of dictatorship. The war concluded with the victory of the nationalist forces led by General Francisco Franco, who then established a long-lasting conservative military dictatorship. The Spanish Civil War, 1936 through 39, was a brutal ideological conflict between the democratically elected Republican government and the nationalist rebels. It was a crucial dress rehearsal for World War II because Germany, under Hitler, and Italy, under Mussolini, openly supplied Franco's nationalists with weapons, planes, and troops. The Western democracies, by contrast, largely maintained a policy of non-intervention, which severely hampered the Republican side. The nationalist victory solidified a fascist-aligned regime in Western Europe and demonstrated the destructive power of modern aerial warfare. For example, the bombing of Guernica. The Einstein-Szilard letter. On August 2, Albert Einstein signed a letter drafted by physicist Leo Szilard and others, advising President Franklin D. Roosevelt of the potential of Nazi Germany to develop a new, extremely powerful bomb using uranium. This letter was critical in initiating the U.S. government's research efforts, which eventually evolved into the Manhattan Project. This letter, addressed to President Roosevelt, did not directly create the atomic bomb, but acted as the trigger for official U.S. government research into nuclear technology. The letter warned that German scientists might already be attempting to harness the massive energy released during nuclear fission. This fear that the Nazis could develop an atomic weapon first is what convinced Roosevelt to create the Advisory Committee on Uranium, which eventually grew into the vast Manhattan Project. The SS St. Louis. This ship, carrying over 900 Jewish refugees fleeing persecution in Germany, was denied entry by Cuba, the United States, and Canada. It was forced to return to Europe, and many of its passengers later perished in the Holocaust. This tragic event became a stark symbol of the world's failure to rescue Jewish refugees. This incident is often called the Voyage of the Damned and serves as a historical case of the restrictive immigration policies of Western nations during the Holocaust era. After being turned away by Cuba and the US, the ship had to return to Europe. While some passengers found safety in the UK, the Netherlands, Belgium, and France, over 250 of the passengers who disembarked in continental Europe were later caught up in the Nazi invasion and perished in concentration camps. While the initial discovery of nuclear fission was in late 1938, in 1939, scientists like Lise Meitner and Otto Frisch provided the theoretical explanation for nuclear fission, a key step toward the development of atomic energy. Nuclear fission is the process where the nucleus of a heavy atom, like uranium, is split into two lighter nuclei, releasing an enormous amount of energy. The experimental work was done in 1938 by Otto Hahn and Fritz Strassmann. However, it was the theoretical explanation provided by Lise Meitner and her nephew, Otto Frisch, in 1939 that correctly interpreted the process. Meitner and an Austrian Jewish physicist, exiled by the Nazis, was instrumental in realizing the immense power potential of the splitting atom. The crucial theoretical explanation was provided by Austrian-Swedish physicist Lise Meitner and her nephew, Otto Frisch, who correctly interpreted the baffling experimental results of German chemists Otto Hahn and Fritz Strassmann. Hahn and Strassmann had observed that when they bombarded uranium with neutrons, they produced the much lighter element barium, which was physically impossible according to the prevailing nuclear model. Meitner and Frisch, applying the quote-unquote liquid drop model of the nucleus, realized that uranium nucleus was splitting into two, splitting in two, a process they named fission. This discovery was world-altering because their calculations showed that this splitting process released a tremendous amount of energy, immediately raising the terrifying possibility of harnessing it for a bomb, which directly prompted the efforts of the Allies and the Nazis. On August 27, 1939, there was the first flight of an aircraft powered purely by a turbojet engine. The plane was the German Heinkel 178, and the engine was designed by Hans von Ohain. Up until this point, all airplanes were powered by piston engines and propellers, which have a theoretical speed limit. The jet engine eliminated the propeller, producing thrust by ejecting a high-speed exhaust gas. This breakthrough, developed by the private company Heinkel, largely in secret, instantly opened the door to aircraft that could fly significantly faster and higher than ever before. Although the plane itself was primitive, and the German Air Ministry initially rejected it, it marked the true beginning of the jet age in aviation, a development that would dramatically influence the air war during the latter half of World War II and all air travel thereafter. The last public execution in France occurred on June 17, 1939. The convicted person was Eugen Weidmann, a German national. He was convicted of multiple kidnappings and murders. The execution took place in Versailles. The method used was the guillotine. The event drew a large, unruly crowd. The public spectacle was deemed sensational and chaotic. The French government was so disgusted by the disorder that it banned all public executions afterward. Executions continued, but were held privately inside prison walls. France abolished the death penalty entirely in 1981. The technology giant Hewlett-Packard, HP, was founded by Bill Hewlett and David Packard in a garage in Palo Alto, California, making an early milestone in the development of high-tech industry in that region. HP's first product was an audio oscillator, a device used to test sound equipment. The first major customer was Walt Disney Productions, which used 8 of their oscillators to develop the revolutionary sound system for the movie Fantasia. Founded in a small garage in Palo Alto, California, HP's establishment is often cited as the symbolic birthplace of Silicon Valley. Their culture of innovation and employee-focused management became a model for future tech startups. The first American football game to ever be televised was played on September 30 between the Fordham Rams and the Waynesburg Yellow Jackets. It was a broadcast by NBC in New York. In the comic book Detective Comics number 27, dated May 1939, the character Batman made his first ever appearance, ushering in one of the most enduring superhero franchises. Unlike Superman, who debuted the year before, Batman, Bruce Wayne, possessed no actual superpowers. His power relied entirely on peak physical conditioning, detective skills, intelligence, and advanced gadgets. Created by Bob Kane and Bill Finger, Batman introduced a darker, more psychologically complex hero to the comic book world, establishing the trope of vigilante operating in the shadows. After being denied the use of Constitution Hall in Washington, D.C. due to her race, opera singer Marianne Anderson gave a monumental open-air concert on the steps of the Lincoln Memorial on Easter Sunday. The event drew an audience of over 75,000 people and became a powerful moment in the American civil rights movement. The concert came about because the Daughters of the American Revolution, DAR, had barred her from singing at their venue, Constitution Hall, due to her race. First Lady Eleanor Roosevelt and Secretary of the Interior Harold Ickes resigned from the DAR in protest and arranged for the concert to take place on the steps of the Lincoln Memorial. The performance was a pivotal and highly visible moment in the struggle against racial segregation in America. The first ever NCAA tournament, known today as March Madness, was played. The University of Oregon defeated the Ohio State University to become the inaugural champions. In India, Mahatma Gandhi began a fast in Mumbai in March to protest the autocratic rule and political practices in the princely states. John Steinbeck's seminal novel, The Grapes of Wrath, was published. Raymond Chandler's first novel, The Big Sleep, was published, introducing the character Philip Marlowe. This year is considered one of the greatest years in Hollywood history, with the release of Gone with the Wind, premiered in December, and The Wizard of Oz. The term telomere, meaning the end part or end section, was coined in 1939 by the pioneering geneticist and Nobel laureate Hermann J. Muller to describe the specialized ends of chromosomes. His work focused on the protective qualities of these ends, noting they were necessary for chromosome stability, essentially naming them for their position at the, quote, end part of the genetic material. Chromosomes are thread-like structures found inside the nucleus of almost every cell in your body. They are essentially highly organized and compact packages of your DNA, deoxyribonucleic acid, DNA, or deoxyribonucleic acid, is a long, complex molecule that contains the genetic instructions used in development, functioning, growth and reproduction of all known organisms. In short, it is the hereditary material, the blueprint, that is passed from parent to offspring. It has a distinctive double helix shape, resembling a twisted ladder. In humans, DNA is primarily located in the nucleus of every cell, organized into structures called chromosomes. The quote-unquote rungs of the ladder are made of 4 chemical bases: adenine A, thymine T, guanine G, and cytosine C. Or adenine A, thymine T, guanine G, and cytosine C. The sequence of these bases forms the code, or the instructions. Specific segments of DNA are called genes, which contain the instructions needed to build proteins, the workhorses of the cell. Chromosomes carry the genetic blueprint genes that determines all the characteristics and functions of an organism. They ensure that DNA is accurately copied and distributed when cells divide. Each chromosome is made up of a single, very long DNA molecule that is tightly coiled and wrapped around proteins called histones. This dense structure allows the huge amount of DNA to fit inside the cell nucleus. Before a cell divides, a chromosome duplicates itself, forming an X shape. These 2 identical halves are called sister chromatids, joined at a central point called the centromere. Normal human cells have 46 chromosomes, 23 pairs, 22 pairs of autosomes, and 1 pair of sex chromosomes, XX for female, XY for male. Chromosome breakage refers to the physical discontinuity or damage in the DNA backbone of a chromosome. X-rays are a powerful agent that can cause this damage, leading to significant genetic consequences. X-rays are a form of ionizing radiation, meaning they have enough energy to knock electrons out of atoms and molecules. This ionization causes damage in 2 primary ways. Direct action, this is less common. The X-ray photon directly hits the DNA molecule, breaking the sugar phosphate backbone and causing either a single strand break or a more severe double strand break, DSB. And indirect action, this is more common. The X-ray photon hits water molecules, which make up most of the cell's volume. This creates highly reactive molecules called free radicals, like hydroxyl radicals. These free radicals then rapidly attack and chemically damage the DNA, leading to strand breaks. The primary concern with chromosome breakage is that If the cell repairs if the cell's repair mechanisms fail, the damaged chromosomes lead to chromosomal aberrations, abnormalities, including that a piece of the chromosome is lost, a piece breaks off and attaches to a different non-homologous chromosome, like the sticky ends Muller discovered. A segment breaks off, flips around, and reattaches backward. These aberrations can lead to cellular death, apoptosis. The damage is too severe for the cell to survive. If the damaged cell survives, the resulting change in DNA sequence can alter genes, which is the link Hermann J. Muller discovered. This increased mutation rate is why radiation is linked to an elevated risk of cancer, and damaged chromosomes may prevent the cell from completing the division process, leading to senescence or death. Geneticist Hermann J. Muller named the structure based on his observations that chromosome ends were specially sealed and didn't fuse with one another after breakage. Muller was studying the effects of X-rays on chromosomes in fruit flies. His work established that the telomere was a distinct, stable entity. This groundbreaking discovery laid the foundation for decades of research into cell aging and cancer, which continues today. Hermann Joseph Muller, 1890 through 1967, was an American geneticist and biologist who made profound contributions to the understanding of chromosomes, mutations, and the effects of radiation on genetics. He is best known for winning the Nobel Prize in Physiology or Medicine in 1946 for demonstrating that X-rays can cause mutations in genes. He coined the term telomeres and was the first to recognize the specialized protective function of chromosome ends. Muller's work primarily involved studying the genetics of the fruit fly, Drosophila melanogaster. In the late 1920s and 1930s, he performed experiments involving chromosome breakage caused by X-ray radiation. He observed that when a chromosome broke, the new ends created by the breakage were highly sticky, quote unquote, and tended to fuse back together or with other broken chromosome pieces. However, he also observed that the natural ends of the original chromosomes were never sticky and did not participate in these fusions. They maintained their integrity and stability. Telomere shortening is the most direct and precise cellular clock. There is the actual genetic material that forms the bulk of the telomere. In humans, this is the simple 6-nucleotide sequence TTAGGG repeated over and over again, thousands of times. The same 6-letter sequence is simply copy-pasted in tandem, forming a long, uniform stretch. It is non-coding DNA, meaning it doesn't contain the instructions genes for making proteins. This repetitive junk DNA is present solely to act as a buffer. Because the DNA replication machinery cannot copy the very end of the chromosome. Because of that, it's these repetitive sequences that get shortened with each cell division, sparing the valuable genetic code, the genes, from being lost. There is also a group of specialized proteins that physically bind to the repetitive DNA sequences. The entire complex of these proteins is often called shelterin. They form a protein coat that covers and protects the DNA ends. These proteins form a closed-loop structure that essentially hides the end of the chromosome. These proteins also signal to the cell's repair machinery that the end of the chromosome is natural and not a break that needs to be quote-unquote repaired by fusing it with another chromosome. Without this protein shield, the chromosome ends would stick together, leading to a massive genetic damage. In short, the repetitive DNA sequences are the part that gets sacrificed, shortened over time, and the protein complexes are the part that protects the whole structure from being recognized as damage. Telomeres are repetitive DNA sequences and protein complexes at the ends of your chromosomes. Every time a normal cell divides to repair or replace tissue, the cell's replication machinery cannot copy the very tip of the chromosome, causing the telomeres to shorten slightly. How exactly do they shorten? The DNA molecule is a double helix, and during replication, the two strands are separated. New DNA strands are built on these templates. DNA polymerase is a crucial enzyme that acts as the master builder or synthesizer of the cell. Its primary function is to create new DNA molecules by assembling nucleotides, the chemical building blocks of DNA, into long chains. It is essential for DNA replication, the process where a cell makes a complete, identical copy of its entire DNA before cell division. It can only build a new DNA strand in one direction, from the 5' end to the 3' end. The terms 5' end and 3' end refer to the two chemically distinct ends of a strand of DNA or RNA. These labels are crucial because they define the directionality of a nucleic acid strand, which dictates how the strand is built or synthesized and read by circular machinery like DNA polymerase. The 5' and 3' labels refer to the specific carbon atom in the deoxyribose sugar molecule that is located at the end of the strand. The sugar molecule is the backbone of the DNA chain, and its 5 carbon atoms are numbered 1' through 5'. The 5' end is defined by the 5' carbon atom of the terminal deoxyribose sugar. Hydroxyl group OH is attached to this 3' carbon. No, I missed some sentences. I repeat, the 5' end is defined by the 5' carbon atom of the terminal deoxyribose sugar. A phosphate group, PO4, is attached to this 5' carbon. In synthesis, new nucleotides are never added to the 5' end. The 3' end is defined by the 3' carbon atom of the terminal deoxyribose sugar. Hydroxyl group OH is attached to this 3' carbon. The 3' end is the growing end of the strand. DNA polymerase and other enzymes can only add new nucleotides, specifically the phosphate group of the incoming nucleotide, onto the free OH group at the 3' end. DNA polymerase and other enzymes can only add new nucleotides onto the free OH group at the 3' end, in other words. The most important concept is that all fundamental biological processes involving DNA, including replication, transcription making RNA, and DNA repair, must proceed in the 5' to 3' direction. When a new strand of DNA is being built, the enzymes always move along the template strand from its 3' end to its 5' end, while simultaneously building the new complementary strand from its 5' end to its 3' end. This strict one-way rule is why the end replication problem at the linear chromosome tips occurs, as DNA polymerase cannot initiate synthesis at the absolute 3' end of the template strand to fill the gap. This directional limitation is the root of the end replication problem related to telomere shortening. Most DNA polymerases have a proofreading ability, allowing them to detect and correct errors, mismatched bases, during synthesis process, ensuring the fidelity of the genetic code. DNA polymerase can only build new DNA strand in one direction, the 5' to 3' direction. One of the two template strands can be copied continuously toward the replication fork. This is the leading strand. The other template strand must be copied in short, discontinuous segments moving away from the replication fork. The replication fork is the specific Y-shaped structure that forms when a double-stranded DNA molecule is being copied, replicated. It is essentially the active site where the DNA is unwound and separated into two single strands, providing the templates for synthesizing new DNA. It looks like a fork or a zipper that is being pulled open. It is the point of separation where the parent DNA helix is unwound by the enzyme helicase. Helicase is a crucial enzyme that acts like a motor to unwind and separate the two tightly intertwined strands of the DNA double helix. It unzips the DNA helix, breaking the hydrogen bonds between the complementary base pairs AT and GC. This action creates the replication fork, providing the two single-stranded templates needed for DNA replication and repair. Going back and repeating the point of digression, the other template strand must be copied in short, discontinuous segments, moving away from the replication fork. This is lagging strand. To start any new segment of DNA polymerase needs a small starter piece called an RNA primer to attach to the template. On the lagging strand, the final segment of DNA requires an RNA primer to sit right at the very end of the linear chromosome. Once the new DNA is synthesized, all RNA primers must be removed. When the final RNA primer is removed from the extreme tip of the lagging strand, there is no way for DNA polymerase to fill the resulting gap with DNA because it cannot start synthesis without attaching a new primer before the gap, which is physically impossible at the absolute end of the linear chromosome. A small portion of the DNA at the very end of the chromosome template is left uncopied and is subsequently degraded. This small uncopied segment is taken from the repetitive telomere DNA, causing the telomere to become slightly shorter with every cell division. The length of the telomere serves as a countdown timer. When the telomeres become critically short, the cell interprets this as severe DNA damage. This short telomere signal immediately triggers the cell to enter a state called cellular senescence, stopping division, or apoptosis, programmed cell death. This initiates the quote-unquote consequence of aging, such as reduced tissue regeneration. The second mechanism through which cells know time has passed is melanocyte stem cell, MCSC. Melanocyte stem cell exhaustion, MCSC exhaustion. Melanocyte stem cells, MCSCs, are specialized, undifferentiated cells found in the hair follicle that are responsible for producing the melanocytes, the active cells that create pigment, melanin, to color the hair. In essence, they are the reservoir of color-producing cells for your hair. They reside in a protected area of the hair follicle called the hair follicle bulge and the adjacent hair germ. Their primary job is to self-renew, create more MCSCs, and differentiate, mature into active melanocytes. They are recruited during the anagen phase growth phase of the hair cycle. They migrate down from the bulge area into the growing hair bulb, where they begin producing melanin. The hair bulb is the enlarged base structure at the very bottom of the hair follicle. It is the most vital living part of the follicle and is often referred to as the hair factory floor. It is a specialized region where the production of the hair shaft itself takes place. The bulb contains rapidly dividing cells called matrix cells. These are the cells that differentiate, specialize, and move upward, hardening into the keratin protein that forms the hair shaft. This rapid division makes the hair bulb one of the fastest growing tissues in the body. Nestled at the base of the hair bulb is the cluster of connective tissue and blood capillaries called the dermal papilla. This structure is crucial because it provides the blood supply, nutrients, and signaling molecules required to sustain the intense growth and division of these matrix cells. The active melanocytes, pigment-producing cells, that migrated from the MCSC niche are located here, surrounding the dermal papilla. They inject the color pigment, melanin, into the developing hair shaft before it hardens. Melanocyte stem cell MCSC exhaustion is the primary biological reason for hair graying, achromotrichia. It refers to the finite lifespan and progressive loss of function of the stem cells responsible for hair pigment. Finite lifespan and progressive loss of function of the stem cells responsible for hair pigment. MCSCs reside in a niche within the hair follicle, a tiny, specialized location that provides the exact conditions, the structural support, specific signaling molecules, and unique cell-to-cell contacts necessary for the MCSCs to remain in their resting, undifferentiated state until they are needed, and are supposed to continuously replenish the active melanocytes, the pigment-producing cells, during each new hair growth cycle. The growth of a hair shaft from its follicle is not continuous. It occurs in a series of distinct, repeated phases, known collectively as the hair growth cycle. This cycle determines the length and health of your hair. The anagen phase is the active growth period. The cells in the hair bulb divide rapidly and the hair shaft is actively produced and pushed out of the follicle. The melanocytes are active during this time, injecting pigment into the hair shaft. This is the longest phase, lasting anywhere from 2 to 7 years, which is why head hair can grow very long. The length of this phase is genetically determined. At any given time, about 85 to 90% of all hair on your head is in the anagen phase. At any given time. The catagen phase is a short transitional period between growth and rest. The hair follicle shrinks dramatically, and the lower part detaches from the blood supply, the dermal papilla. the hair shaft stops growing and becomes a club hair. This phase is very brief, lasting only about 2 to 3 weeks. Only about 1 to 2% of all hair is in the catagen phase. The telogen phase is a period of rest and shedding. The hair follicle is completely inactive. The club hair is held in place. The follicle essentially rests until it is ready to begin a new cycle. This phase typically lasts around 2 to 4 months. About 10 to 15% of all hair is in the telogen phase. Some sources describe a fourth phase, exogen, which is sometimes considered part of telogen. This is the phase where the old resting club hair is shed, falls out, usually facilitated by daily brushing or washing. It occurs just before or as the follicle begins a new anagen growth phase. The cycle repeats itself up to 20 times over a person's lifetime. The exhaustion of the melanocyte stem cells, MCSCs, happen because they failed to correctly perform their renewal and migration role across these repeated cycles. Over decades, these stem cells gradually lose their ability to mature and migrate into the hair bulb. This failure to differentiate and move into the correct location means that when a new hair strand begins to grow, there are no active melanocytes present to inject melanin, color pigment, into the hair shaft. Consequently, the new hair grows out clear or white, leading to the overall appearance of graying hair. This process is largely driven by genetic factors that program the limit on the number of times these stem cells can successfully execute their replenishment role. The MCSCs, which supply the pigment-producing cells for the hair, have a limited number of times they can migrate and differentiate. This process is tightly linked to the repeated cycles of hair growth. After a number of hair cycles, dictated by genetics, the MCSCs simply fail to maintain their niche in the hair follicle. The MCSC niche is primarily located in the area called the hair follicle bulge and the adjacent hair germ. This niche acts like a shelter or a safe house that protects the stem cells from environmental damage and signals that would cause them to die or mature prematurely. It's where critical chemical signals, like specific growth factors, are exchanged between the stem cells and their surrounding structural cells. These signals regulate when the MCSCs should remain quiescent, resting, and when they should become activated to produce pigment for new hair growth. So as the MCSCs simply fail to maintain their niche in the hair follicle, they can no longer travel to the growing hair bulb. It's a matter of exhaustion of a finite resource. When a hair follicle enters a new growth phase, if there are no active melanocytes present because the stem cells didn't replenish them, the new hair grows out clear or white. Now, cells get to know that aging happened this way. But when they do, how exactly does it initiate the process? And the initiation would be the damage accumulated by the body over decades. 1. Oxidative stress and free radicals. Normal metabolism, especially in the mitochondria, the cell's power plants, constantly produces highly reactive molecules called free radicals. For example, reactive oxygen species. While the body has defense enzymes, over time the production of free radicals outpaces the repair and defense mechanisms. This accumulation of molecular damage is known as oxidative stress. This stress acts as a toxin, directly damaging cellular machinery. In the context of hair graying, the accumulation of hydrogen peroxide, a powerful free radical, directly destroys the melanocytes and breaks down the enzyme needed to make melanin, forcing the DNA is constantly being damaged by free radicals, radiation, and replication errors. Forcing hair to turn white. The DNA is constantly being damaged by free radicals, radiation, and replication errors. 2. DNA damage accumulation. DNA is constantly being damaged by free radicals, radiation, and replication errors. It was a part of this one, the DNA damage accumulation, not the previous one. The body's DNA repair systems gradually become less efficient with age. As unrepaired mutations accumulate, the cell's blueprint becomes faulty. Cells start producing defective proteins, stop carrying out their functions correctly, like making pigment, or turn cancerous. That's it. Therefore, aging is a cascade of failures driven by 2 forces: programmed obsolescence. Cellular components like telomeres and stem cells have built-in limitations, and cumulative damage. Molecular wear and tear, oxidative stress overwhelms the repair systems. Achromotrichia is primarily due to the gradual cessation of pigment production in the hair follicles. A hair follicle is a tiny tube-shaped structure located in the skin, epidermis, and dermis, from which a hair shaft grows. It anchors the hair into the skin. It manufactures the hair shaft using rapidly dividing cells in the hair bulb. It determines the hair's color and texture, and it regulates the hair growth cycle. The color of your hair is determined by a specialized type of cell called melanocytes, which are located in the hair follicle. Melanocytes produce the pigment called melanin. There are 2 main types: eumelanin, which gives hair black or brown shades, and pheomelanin, or pheomelanin, gives hair red and yellow shades. The combination and concentration of these 2 pigments determine your unique hair color. When a new hair grows, the melanocytes inject melanin into the keratin-producing cells that make up the hair shaft. As the hair grows out, it maintains this color. Over time, 2 key processes cause the melanocytes to stop functioning properly. 1. Melanocyte exhaustion. The primary reason: melanocytes, like other cells, have a finite life cycle and a limited capacity to divide and sustain pigment production. The hair follicle contains melanocyte stem cells, MCSCs, that continuously replenish the active melanocytes. As we age, these stem cells gradually lose their ability to mature and migrate into the hair bulb. When a hair follicle enters a new growth cycle, if the MCSCs fail to replenish the active melanocytes, the new hair shaft grows without any pigment, resulting in white or clear hair. 2. Oxidative stress and hydrogen peroxide. A natural byproduct of cell metabolism is the production of reactive oxygen species, including hydrogen peroxide, H2O2. As we age, the body's ability to neutralize this hydrogen peroxide diminishes. Hydrogen peroxide is a powerful bleaching agent. The accumulation of H2O2 around the hair follicle effectively bleaches the melanin that has already been produced and also damages the enzymes, tyrosinase, that melanocytes need to manufacture new melanin. The age at which a person starts to gray is largely determined by genetics. If your parents went gray early, you are likely to as well. Ethnicity is also a factor. Graying typically starts around the mid-30s for Caucasians, the late 30s for Asians, and the mid-40s for Africans. Certain conditions, like pernicious anemia, thyroid disorders, or vitiligo, can lead to premature graying. While chronic stress has been linked to accelerated graying, it's not the primary cause. It may temporarily deplete MCSCs, but genetics drive the long-term process. In essence, hair turns white because the microscopic pigment-producing machinery within the hair follicle simply runs out of steam and is unable to maintain the constant supply of melanin needed for color. The hair itself is clear. It only appears white or gray due to the way light reflects off the unpigmented strands.